y ya Diego Valera y Michel Mayor, ya podéis pasar que yo ya me retiro. Gracias.
Buenas tardes. En primer lugar, pues me gustaría agradecer a todas las personas e instituciones que hacen posible la celebración de las jornadas astronómicas en Almería, especialmente pues a Pedro San José, que es el alma mater de la jornada, y como no al Ayuntamiento de Almería y a la Diputación de Almería, que siempre pues están realizando actividades tan interesantes como las que nos reúnen esta semana, que afortunadamente tenemos un clima infinitamente más favorable que la última vez, que tuvimos que venir a nado, pero con todo y con eso estuvo la sala llena como hoy. Hoy comenzamos una semana intensa que pone a Almería en el mapa mundial de la astronomía. La Universidad de Almería siempre apoyará iniciativas científicas como estas jornadas que tanta relevancia e interés despiertan pues, entre todos los almerienses. Es para mí un honor presentar a Michel Mayor, uno de los más reputados físicos de la actualidad. Michel nació en Lausanne, Suiza, donde estudió física, doctorándose en 1971 en el Observatorio de Ginebra. Ejerció como investigador en el Instituto de Astronomía de la Universidad de Cambridge, en el Reino Unido, y posteriormente en el Observatorio Europeo Austral, en el norte de Chile. También ha sido investigador en el Instituto de Astronomía de la Universidad de Hawái en Estados Unidos. Desde 1998 es profesor del Departamento de Astronomía de la Facultad de Ciencias de la Universidad de Ginebra. Además, desde 1998 hasta 2014 fue director del Observatorio de Ginebra. Previamente, en 1995, junto a su alumno de tesis doctoral Didier Queloz, descubrió 51 Pegasus B, primer planeta extrasolar que orbita una estrella del tipo del Sol. Lo hizo desde el Observatorio de la Alta Provenza, al sur de Francia, utilizando instrumentos personalizados. Este hallazgo inició una revolución en la astronomía, encontrándose desde entonces con una multitud de exoplanetas en la Vía Láctea. Por todo ello, en 2019 fue galardonado con el Premio Nobel de Física junto a su alumno Didier. Ambos fueron recibidos hace unos meses, exactamente en octubre de 2021, en audiencia privada por el rey Felipe VI, que es muy aficionado, como saben, a la astrofísica. Ha recibido muchos e importantes premios en su carrera científica, tiene un listado muy extenso en todo el mundo, es súper reconocido, y su pensamiento sobre la vida del universo se resume en una frase. Dice: creo que la vida es algo común en el universo, donde hay miles de millones de tierras. Estos días atrás tuve la osadía de cotillear un poco su currículum y su producción científica en Scopus, que como saben es una base de datos reconocida a nivel internacional, y me quedé absolutamente encandilado e impactado. Su producción científica es extraordinaria, posee casi 500 artículos científicos en revistas de impacto, ha sido citado casi 40.000 veces, y tiene, valga la expresión, un estratosférico H-index, que es lo que mide un poquito pues, el nivel de cada uno de los científicos. En España, un catedrático de universidad reconocido estará con un H-index de 20, 30 y algo. Pues Michel tiene 100 y pico, exactamente 102 de H-index, lo que da una idea de la relevancia de mi compañero de mesa. Es para mí desde luego un privilegio estar hoy aquí presentándolo. Michel, we are delighted to have you in Almería. It's an honor for all of us to be able to meet you. We look forward for hearing from you. You have the floor.
Merci, muchas gracias. Okay, good evening, ladies and gentlemen. I'm really sorry not to be able to speak in Spanish. So it's the reason why we have John Beckman with us to translate and to...
Oui, para traducir y para pedir quizás que se bajen los focos, porque La presentación
Yes.
oui.
It's visible for you? Okay, so 27 years ago we started a new chapter of astrophysics, and right now many thousands of people are involved in this new chapter, and I will try this night to give you some hints of what is going on.
Pues hace 27 años empezaron un proyecto para medir, detectar planetas, y nos va a dar un poco de la historia y una explicación.
So we are not the first to ask questions related to this kind of problem. It's very strange and amazing to see that already at the time of the Greek philosopher, for example, we have this very famous letter from Epicurus on the 4th century before Christus. And in this very long letter, he wrote, worlds are in an infinite number, some of them similar to our own one, some other very different. And later, in the same letter, he said, living species could exist in some worlds and could not in others. It's incredible. Let's imagine these people doing this. The quantity, the idea behind worlds is not exoplanet. It was just more philosophical and general question. But nevertheless, and you see that I've indicated here two names, Le Cid and Democritus, already before was discussing this kind of matter.
Sí, el filósofo Epicuro especuló que podría haber un número infinito de mundos, sin definir lo que es un mundo, y que pueden ser similares a los nuestros, y pueden ser diferentes y pueden tener vida. Y claro, esa especulación es muy resonante.
And contrary to what we can dream or believe, that this idea was dead and not maintained during the Christian period. But this is not the case. You can find, I will not give a complete historical talk here, but you have a lot of theologians, philosophers having discussed this kind of matter during the last two millennium. And I will give only one or two citations. For example, there's a very important philosopher or theologian of the end of the Middle Age, Albert the Great, Albertus Magnus. He said, do there exist many worlds or there only one? This is one of the most noble and exalted questions in the study of nature. And the second point I will just stress is the Bishop of Paris, just after the creation of the Sorbonne in Paris. He asked the permission to the Pope, Jean XXI, to have the permission to teach and to discuss in Sorbonne the hypothesis of the plurality of worlds. I will okay, we have dozens of citations we can mention, but just these two is already enough to demonstrate the interest of this question.
Voy a mencionar solamente unos pocos pensadores que han especulado sobre la posible presencia de otros mundos. Está el San Alberto el Grande. Si existen muchos mundos o es solamente hay uno. Esa es una de las preguntas, las cuestiones más nobles que hay en la naturaleza. Y Etienne Tompier, el obispo de París, dijo que en la nueva creación, la Sorbona, Universidad, que era muy importante estudiar la pluralidad de los mundos.
This idea, very promoted after the ideas given by Giordano Bruno, that you could have planetary system around other stars. I found this image of a very old atlas published by Doppelmayr a little bit more than 200 years ago. You see this is the old style astronomical with a solar system in the middle, and look in the upper right corner, and here what you see? You see that the distant stars outside the solar system, several of them are surrounded by planetary system. And this was already, I would say, popular more than 200 years ago.
Ese atlas del siglo XVIII se nota que hay el espacio dibujado estrellas y alrededor de las estrellas planetas, y eso implica que todo el mundo estaba pensando en esta posibilidad.
So, now really, we can move to the modern time. Probably most of you know that our sun, our solar system, is part of a very big system of something like 2 billion stars, similar to the sun, a little bit more bigger or smaller. This is not a problem. But this huge sample of stars are rotating, linked by the gravitation of these stars. And they rotate, and you have this beautiful structure. And you can notice along the arm of this structure some pink dot. Evidently it's not a star at this size, because it's not possible to see stars individually. But I will discuss this point later. Evidently this is not our own Milky Way, because the distance is much too big. It's not possible to go on, take a picture and go back. So this is another galaxy similar to our own one.
Entonces, para resumir, esta foto preciosa es una galaxia similar a la Vía Láctea y tiene billones de estrellas, y también tiene algunos puntos rosados en los brazos, que él va a hablar un poco de estos más tarde. Obviamente no podemos salir fuera de nuestra galaxia, sacar una foto y volver, entonces tenemos que hacer la foto de otra galaxia.
And look ideally in a small piece of the galaxy. Right now I'm cheating a little bit, because I will take a real photography of our own galaxy, and this is what you can see. If you take a picture on the Milky Way, you can see this huge number of stars. So the question is not to find new stars, we have plenty of them. The problem is to ask if some planets are orbiting all these small dots here.
Sacando una foto de una pequeña parte de nuestra galaxia, la Vía Láctea, está plena de estrellas. La pregunta no es buscando las estrellas, sino ver si quizás hay planetas alrededor de todas estas estrellas.
It's very strange. If more than 200 years ago it was common to paint some exoplanet, some other planetary system around stars, okay? In fact, if you are looking in the literature in astronomy during the 20th century, here you have a diagram where you have the number of estimated number of planetary system as a function of years. And you see that before the middle of the 20th century, astronomers do not believe that we have other planetary system. You have a very famous, important name of astronomers like Sir James in Cambridge, Shapley in Harvard, and so on. And all these people have some reason to say, no, our own solar system is alone, is single maybe Europe in a second, but not. But the idea changed in the middle of the century, first for some bad reasons, but I will not discuss this here. And then after people advanced the good reason, they found the reason why you need to have a disk of dust and gas to form planets. And this was missing in the middle of the 20th century, and the reason was found only after 1952, and then after you jump to, it's a logarithmic diagram, so here we are at the level of 10 billion, 100 billion, something like this. So this is compatible with a sentence like all stars have planetary systems.
Pues gráfica es de las predicciones de los astrónomos importantes sobre si hay planetas alrededor de las estrellas durante todo el siglo XX. Al principio del siglo XX, hasta la mitad, la mayoría de los grandes astrónomos pensaban que no, que nuestro sistema solar era el único. Pero había un elemento que faltaba en la idea de cómo se forma una estrella. Ese elemento que faltaba es que cada estrella al formarse tiene un disco de polvo y gas fino alrededor. Una vez que esta idea cuajó, entonces los teóricos empezaron a decir que sí, que es muy probable que hay planetas alrededor de las estrellas en la segunda mitad, antes del descubrimiento.
So, I'm going back to Orion Nebula. This is a typical big giant molecular cloud. When I say it's a big cloud, it's something like 100,000 times the mass of the Sun. So it's really a big, massive piece of gas. Sometimes, due to different physical mechanisms, you have a collapse of this cloud with a lot of turbulent magnetic fields and things like this. And this is the reason why you have the possibility to form new stars. But as you have a lot of turbulence, you always have an excess of, I would say, angular momentum, maybe let's say rotation. So the gas falling down to the young stars is rotating too fast, and part of the gas will form a disk. And this disk is eventually the nursery to form new planetary systems.
Las estrellas nuevas se forman en las nubes moleculares gigantes que pueden tener, dijo Michel, 100.000 hasta 100.000 veces la masa del Sol. De hecho, las hay mucho más grandes incluso. Y cuando las estrellas se forman, una parte de la nube se colapsa y forma la estrella. Pero siempre hay un poco de rotación. Y esta rotación implica que la estrella gira al formarse y que también hay este disco de rotación en su plano, y esa es la forma de formar los planetas.
This is, I would say, some kind of basic physical mechanism. And so, a priori, we can expect that the almost 100% of stars should have planetary systems. And now, after the question is, do we have a chance to detect this planetary system? But maybe before giving asking for the translation, here you have the same image of Orion Nebula, here on the left. And in 1995, the Hubble Space Telescope observed you have some stars just formed here and moving out of the nebula. And if you are observing these young stars with the Hubble Space Telescope, with a huge resolution of this telescope, you have these images here. So you can see directly the disk of dust and gas surrounding the young star. So this is the proof that we have here all the conditions for the formation of planetary systems orbiting all young stars.
Entonces, cuando el telescopio espacial Hubble, con su magnífica resolución, empezó a tomar imágenes de estrellas formándose, en este caso en la nebulosa de Orión, entonces se detectó directamente estos discos alrededor. Cuando una estrella sale de la nube, si está dentro de la nube original no se detecta, pero al salir de la nube se detecta y su disco se detecta. Entonces la prevalencia de estos discos era la pista más importante que probablemente todas las estrellas al formarse también tienen las condiciones para formación planetaria.
So, I was teaching physics during many years, so I cannot avoid to try to explain things. So some of you know the name Doppler effect, but do not know what it is exactly. It's very, very easy to see and to feel what it is. Let's imagine you have a small insect jumping on a piece of water. Eventually, one jump every second. You have some waves moving away here, circular waves. Let's imagine now that the insect is moving pop, pop, pop. So eventually you can have this image that the waves are with much shorter distance between them in front of the motion and exactly the opposite on the other side. This is simply the Doppler effect. And this is valid for this kind of hydrodynamics phenomena. It's valid also for acoustic waves, the sound of the train arriving and leaving, or it's also possible the same phenomena for the light.
Michel acaba de explicar el método que él utilizó para detectar velocidades en estrellas con planetas. Eso se llama el efecto Doppler. Y simplemente cuando un objeto se mueve hacia nosotros, su luz se hace un poco más azul. Y cuando va hacia en otra dirección, su luz se hace más roja. Y este es el efecto que se hace en el sonido, con un tren que se acerca y se aleja. También en este caso de las ondas en agua. Y este efecto, el efecto Doppler, es lo que ellos utilizaron para detectar los planetas utilizando movimientos de las estrellas.
So, because maybe I have to mention one point. If you look at some distance, the solar system, you have the sun, let's imagine you have the Earth here. The Earth is only reflecting a very small part of the luminosity of the sun. In the visible, the ratio is 1 billion. So at some distance, all things are confused. You have no chance to see the planet. So this is the reason why we have to develop an indirect technique. And this technique is the Doppler effect. So here you can notice that you cannot see the planet, but the star is rotating around the gravity center of the system. So if you measure the velocity of the star, you see sometimes the star is moving in your direction, sometimes in the other direction, and so on. So the wavelengths will oscillate like this. I will go back later. It's much, much smaller than here, and happily we have a huge number of atomic lines in the spectra, giving some reference to measure what should be the normal position of this line if the star is not moving. If the lines are a little bit away, you can measure the velocity.
no se puede, si alguien está intentando detectar la Tierra desde lejos, la luz del Sol lo hace imposible. La luz del Sol es tan brillante que la Tierra no se ve. Pero un planeta alrededor de una estrella causa un pequeño movimiento de la estrella alrededor del centro de gravedad de la pareja. Y esto se nota midiendo el espectro. El espectro oscila durante un periodo de rotación del planeta. Las líneas espectrales de la estrella se mueven por un lado y por otro con frecuencia regular, y eso te permite detectar la presencia y la velocidad también del planeta.
So we have developed with some of colleagues from France a new instrument, a new spectrograph, to precisely measure this atomic light, the light of the stars. And we have selected a large number of stars similar to the Sun, and we start to measure. We measure the velocity, we remeasure the day after, 1 week after, and so on. And at some point, you have some point not with a stable velocity. And for one star, already 27 years ago, the velocity was exactly changing, but with a period of only 4.2 days. And if we estimate the mass is half the mass of Jupiter, so something like 150 times the mass of the Earth. So a gaseous giant planet, but so close to the star to our orbit in only 4 days. This was a beginning of our problem, because the theory said we cannot have a planet, the gaseous planet, with a period so short. It should be at least 10 years. So this is a discrepancy of about 1,000 with the theory. So this was part of the problem. And then after, evidently, this field exploded during the 25 last years, and today we have 5,000 planets discovered.
Entonces, con un instrumento espectrógrafo para medir estos efectos de movimiento, el efecto Doppler, miraron un grupo grande de estrellas, la velocidad medida día tras día tras día tras día, acumulando, y solamente en una de las estrellas se encontraron este efecto de variación exactamente irregular, con un periodo de 4,2 días solamente, y se puede calcular la masa de la mitad de la masa de Júpiter. Y la teoría ha hecho muchas dudas sobre si un planeta tan cerca de su Sol podría sobrevivir, con lo cual era controvertido al principio, pero ahora todo se ha abierto y hay más de 5.000 planetas descubiertos.
Evidently, it was a so huge discovery that we have been stimulated to develop new instrumentation, and then after we increase the precision by a huge domain. For example, this is only what we did in Geneva. 40 years ago, something like this, which we had a precision of 300 meters per second, the velocity of a plane, a jet. Energy used to discover the first planet was 13 meters per second. It's the velocity of a small bike. Currently, our job after 2 arcs, this is a new generation of spectrograph put in operation on the 3.6 meter telescope in Chile and La Palma, and we achieve 1 meter per second. It's typically the velocity of a layman. A man working is typically 1 meter per second. And the last of this series, espresso, is done on top, I will go back to this point, on top of the Mont Paranal in Chile, achieve 0.1 meter per second. So you can see the change of the velocity of star to, let's say, to 100 light years moving at this velocity like this. So this is a difficulty, technical difficulty. And this is actually, a huge project during the last 40 years. And I would mention that not too far from here, at Calaralto, the spectrum of Carmenes is part of this generation here. Achieve always this kind of precision.
Pues la gráfica da el progreso solamente concentrado en el grupo de Michel Mayor. Hay otros grupos, otros experimentos, pero eso es para mostrar el progreso en la precisión de la medida de la velocidad, empezando con 13 metros por segundo y llegando al final a 0.1 kilómetros por segundo, que literalmente, metros por segundo, perdón, que literalmente es poder medir la velocidad de la estrella a 100 años luz con esta velocidad, diferencia de velocidades. Son logros técnicos magníficos y claro, en diferentes telescopios y eso ha dado lugar al descubrimiento de muchos planetas.
And obviously, if we are doing this kind of effort to develop new instruments more and more precise, is the fact that the precision is directly the key to detect very small planets. If you have a star like this, if you have a big planet, okay, you can shake a little bit the motion of the star, but if you have a very small one, the motion will be very small. So this is the way to detect Earth-type planet.
El incentivo de mejorar la resolución es para poder detectar planetas pequeños, porque un planeta grande efectúa un cambio de velocidad más grande en su estrella. Un planeta como la Tierra necesita mucha más precisión y por eso han ido cada vez más y más hacia precisión muy alta.
And now, forget for a moment radial velocities and spectroscopy, and have a look at 5,000 meters north of Chile on an altiplano, Europe with the US, with Japan, have developed an incredible instrument of something like 60 antenna dishes, 12 meters wide, so it's something like the size of this room, and distributed on the altiplano with the capability to coordinate and to collect all the signal received by these different antennas. This is called an interferometer, to achieve a very, very high resolution, a high capability to see small details. And this is working in the sub-millimeter. It's a little bit shorter wavelength compared to the television wavelength.
Ahora está cambiando totalmente de técnica, ha dejado la espectroscopía y nos lleva a Chajnantor, un sitio en Chile, norte de Chile, a 5.000 metros sobre el mar, donde hay un telescopio ALMA que se compone de 60 antenas, cada antena del diámetro de esta sala, conectadas entre sí para formar un telescopio llamado interferómetro, cuya resolución en ángulo en el cielo es muy, muy, muy fino. Y eso es para detectar pequeños detalles en objetos astronómicos.
This is just to show this beautiful country. So, few years ago, evidently this instrument is mostly devoted to study cold gas in the universe. Formation of galaxies, formation of stars, formation of planets, for example, and gas interstellar. So they have decided to look on this small cloud here It's something similar to the Orion Nebula, but much smaller. And because we knew that you have young stars in the middle. This is a normal picture. And after they use the interferometer, and you see the same cloud here with these young stars in the middle, and when you look with the interferometer, this is with a huge capability to see the detail. You can see the star is surrounded by a disk of gas and dust, but what is still more impressive, that you can see that the matter is missing here. 1, 2, 3, 4, 5, at least, I don't know. This because when you form a planet in the disk, the matter will be accreted to form the planet, but will be create this kind of structure like this. And so this is the formation of a young planetary system with 5 or 6 planets.
Pues ALMA está diseñado para detectar objetos fríos que incluyen galaxias en formación, estrellas en formación y planetas en formación. Entonces nos ha mostrado un pequeño disco ya mirado en el cielo antes con fotos normales, pero con ALMA se detecta este disco roto en círculos, dividido en círculos, y que se puede, es un disco de gas y de polvo interestelar, y en cada círculo, cada franja anular, se está formando un planeta. Ese es un sistema planetario en formación.
Indeed, it was still so interesting that these colleagues made a lot of young stars, and this is a picture of this observation, and you see this is very common here. You see this structure. Okay, the details are different, but you see that it's very common to see the structure of the formation of planetary system.
Entonces, una selección de observaciones de diferentes estrellas en formación revela este tipo de estructura de disco roto en anillos donde se forman planetas.
So, we turn now to my own interest. So, obviously, after the detection of the first, and we have detected 7, in fact, from all Provence Observatory in the north, but we have decided to develop a new instrument called ARPS. It's a vacuum spectrograph with a lot of technical improvement, and we have put in operation this instrument with much higher sensitivity to La Silla, north of Chile, also with a 3.6 meter telescope. So the mirror is so big here, and this is absolutely, because this is very strange. ESO asked who would like to develop an instrument with the possibility to measure 1 meter per second. So nobody did this before. So we replied to these things because we believed that it was possible, and the contract was, if you succeed to do it, we will receive a lot of lights. So we have to pay all the material, all the manpower to build the instrument, to prove that it works, and then if it works, we receive 500 lights of a big telescope. It's a huge contract. So this is the reason why during 5 years we have been able to do a huge program to study planets in the southern sky.
En consecuencia de sus primeras detecciones con su instrumento en el norte, en Francia, ellos hicieron muchas mejorías en la técnica y consiguieron otro instrumento, HARPS, que está en Chile, en el Observatorio Europeo Austral, y los gobernadores de eso decían que si podían producir un instrumento capaz de detectar 1 metro por segundo, ellos pueden tener 500 noches en el telescopio. Y era un desafío y lo superaron, y con tantas noches en un telescopio, esa es la envidia de todos, pero la hicieron y me dieron muchos planetas.
I will not describe all the objects we have discovered, several hundred. I will just show one object here. It's with a small number in the catalogue, there's nothing special to say. But you see, here you have a plot where you have the velocity as a function of time here. So this is one season, another season, and so on. So it's 1 year, 2 years, 3 years, so on. And every time you measure the velocity, you put one red dot in this diagram. And after 7 years, something like this, 6 or 7, you can see this kind of thing. The red dots have a shape, something like this. So you see, aha, we have a planet with 7 years of period. But if you give all this data to a computer using a clever program and so on, it say, no, you have 7 planets here. One with 1.1 day and 1.5 mass of the Earth, another one with 6 days, 13 mass, and so on and so on. So several planets very close to the star, some a little bit further, and what you see is the long one. This by eye, you can see this one here. So you see, this is typical of what we have discovered. A huge number of multi-planetary systems, and you see this, when you separate the effect of all, these are the shape of the velocity due to this kind of object. This is typically what we did during 7 years.
Pues entonces nos enseña este ejemplo como típico, aunque solamente uno de muchos. Nos mostró los datos tal y como se miden y después que dan una impresión de variabilidad de velocidad muy mezclado, pero si aplicas un programa para buscar frecuencias, ese programa encuentra múltiples frecuencias, múltiples periodos, entonces múltiples planetas alrededor de esta estrella, y con análisis correcta encuentran un grupo de planetas con un juego de datos, con muchos diferentes periodos.
So, okay, if we have look back to the last 25 years, what we have discovered? Okay, we have proven that exoplanets exist. We have discovered the migrations, this very important phenomena that planets are moving to different periods, much shorter, and we have discovered what is called the diversity of planetary systems. They are not similar to our own one. You have sometimes period of planetary system as short as few hours. You have mass sometimes much bigger than Jupiter's mass. You have eccentric orbit. Some orbits are in the solar system. Jupiter, Saturn, and others are almost circular orbit. But here we have some planets with an orbit like this, very elongated. You have some planets we have discovered having an orbit in the Belsas. The star is rotating in the one direction and the planet in the other one, and so on and so on. And as a consequence, you have a large diversity of the internal structure. Some are so close to the star, so they should be lava planets completely, rock are completely melted. And others, many different kinds of planets.
Entonces, han detectado no solamente muchos planetas, sino muchos tipos de planetas en muchas condiciones. Por ejemplo, planetas con periodos de horas, el periodo del planeta es su año. Entonces, estos planetas están tan cerca de las estrellas que su año es un par de horas o unas pocas horas. Y eso implica que están tan cerca que sus temperaturas son altísimas y entonces le llaman planetas de lava porque hasta la roca se derrite y está claro que es casi un planeta de roca líquida. Y también tienen planetas con órbitas no solamente en un plano sino fuera del plano. Todo tipo de órbitas mezcladas. La variedad es la palabra.
And as we have planets with very short period, this indicates that the planet is very close to the star, so the probability that time to time the planet will cross the disk of the star between your eyes and the star. So this, we can use the terminology, it is an eclipse. In the case here, we are using the terminology is a planetary transit. So we cannot see the planet, but if you measure precisely the luminosity of the star, you have some deep like this, periodic deep, and the depth of the deep is directly an indication of the size of the planet.
Entonces, si un planeta está muy cerca de su estrella, es muy probable que al orbitar pasa directamente delante de la estrella e interrumpe la línea de visión a nosotros. Cuando ocurre una pequeña fracción de la luz de la estrella se corta y si mides la luz de la estrella con gran precisión, no mides el planeta, pero notas el bajón y la subida, bajón y subida de la luz. Y eso te permite medir el tamaño del planeta.
The diameter of Jupiter is about 1/10 of the diameter of the Sun. Let's imagine you are very far from the solar system. If Jupiter crosses the disk of the Sun, it will block the light of 1/10 times 1/10, 1/100 of the. So you will a deep of 1/100, very small. If the Earth crosses the disk of the Sun, this will be, the Earth is about 1/100 of the size of the Sun. So 100 times 100 is 10 minus 4. 0.1 million. So it's a very, very small change of the luminosity. No way to observe this from the ground. But here you see, in 2000, we have discovered, or in 1999, we have discovered an object with a period of 3.5 days. I was collaborating with US colleagues, and one of them, Tim Brown, as an amateur, had a small 10 centimeter telescope in his garage. And he measured with the CCD, and exactly at the time predicted by our own measurement, he observes the dip of a little bit more than 1%, so it is a Jupiter-type planet. And this US colleague reapplied to get time from the Hubble Space Telescope the year after. And you see the quality of the measurement you can have when you are out of the Earth's atmosphere. Fascinating, you see, it's so perfect. So immediately you have the good idea. Oh, if it's possible to have this precision, we can try to detect Earth-type planet from the sea.
Entonces acabo de explicar el otro método principal de detectar exoplanetas. Dijo que si un planeta es el tamaño de Júpiter y lo vemos desde lejos y pasa delante de su estrella, corta 1% de la luz de la estrella, eso se puede medir. Un planeta del tamaño de la Tierra efectivamente corta la 10 milésima parte de la luz de la estrella, eso es más difícil de medir y posiblemente se puede medir. La primera observación en la diapositiva es de un planeta que ellos habían descubierto utilizando el efecto Doppler y que después colegas lo midieron utilizando un telescopio pequeño y detectó este bajón en su luz. Entonces el grupo de Michel pidió tiempo con el telescopio espacial Hubble, donde la precisión es mucho mejor, y midieron esto con precisión asombrosa. Entonces, desde entonces se sabía que usar telescopios en el espacio era la forma de detectar muchos planetas por este método.
So this is just a small graphic to explain what we can. Here this is a star, and you have the planet orbit like this. When the planet is in front, the decrease of the luminosity gives the possibility to determine the diameter of the planet. Okay. When the planet is behind, and you have a satellite measuring the infrared radiation, you have a small decrease of the infrared luminosity because the atmosphere of the planet is very hot. So you have the possibility to measure the temperature of the planet, of the atmosphere of the planet. But what is the most interesting is this small ring blue line. What it is? You have the atmosphere of the planet here, and when you compare the spectrum of the star when the planet is in front or behind, you have a small difference. And this small difference is because the atmosphere of the planet will filter the luminosity of the star. And this gives some information of the chemical composition of the atmosphere of the planet. I will go back because this is the future.
Entonces, con el método de tránsitos, el más simple es detectar el diámetro del planeta por el bajón, el tamaño del bajón. Pero eso es cuando el planeta pasa delante. Cuando el planeta pasa detrás, la luz total baja un poquitín y este bajón se optimiza en el infrarrojo porque el planeta es más frío, entonces emite un infrarrojo más. Entonces, que se puede utilizar también para medir la temperatura del planeta, este bajón cuando el planeta pasa detrás. Pero lo más interesante de todo es que cuando el planeta está delante, una parte de la luz, una pequeña fracción de la luz de la estrella pasa por la atmósfera del planeta. Y utilizando la espectroscopía, uno puede medir la diferencia en esta fase y en la fase cuando el planeta no está. Y eso es capaz de dar las líneas espectrales muy débiles, pero se pueden observar para detectar la química, la estructura química de la atmósfera.
This was a play already from almost 20 years, but I would show a little bit more because you see that you have some reference. They have discovered the sodium, the hydrogen, atomic, water, carbon dioxide, and so on, methane, and so on. But what is the most spectacular? Let's imagine you are observing in a wavelength where the matter of the atmosphere is very opaque. So the disk of the planet looks big. So the contrast will be deep here. Let's imagine you are using another wavelength where the radiation can go through the atmosphere of the planet very deep. So apparently the planet is much smaller in this wavelength. So in such a case it's like this. So simply to measure carefully the diminution, the deep of the luminosity at different wavelengths, you can use spectroscopy. You can analyze the chemistry of planets. Incredible.
Bueno, entonces, si observas con un filtro con una longitud de onda, ves un bajón. y con otra longitud de onda ves otra profundidad de bajón según la longitud de onda. Y eso es porque la atmósfera tiene transparencia diferente en función de longitud de onda, a causa de los constituyentes. Si pasa por una onda con una molécula fuerte, entonces es más aparto. Si tú puedes combinar observaciones en muchas longitudes de onda, hacer espectroscopía y poder detectar moléculas individuales en la atmósfera.
And evidently, if you are in space, it's much better. You are outside the atmosphere. So this is a plot, not the last one. It's a plot made by the discovery of the Kepler space mission. It's about 1 meter telescope in space, and the idea is extremely simple. Let's imagine this is a star, the Earth. This is a Kepler satellite, and it's looking some place in the sky, orbiting the Earth like this, taking a picture of the field of stars every, I don't know, minute or something like this. And then after 3 years, you have a long series of measurements made of something like 100,000 stars. So you let the computer to analyze the things, and the computer will find some stars with periodic dip, okay? In such a case, you have the radius versus the period, you put a small black dot here. And sometimes you have very complicated pattern. It's not only one single dip, but different families of dip with different period. And this indicates that you have a multi-planetary system. And so, for example, I will describe the red one here. For this object here, with a period of about 100 days, you have 6 planets turning over with different periods. And you see, and this red is used for 6 planets, blue for 3 and so on, yellow for 4. So you see, multi-planetary system, like the whole solar system, are extremely frequent in the universe. And I do not pretend that these kind of objects are single planets, but sometimes you have only a small difference of orbits between the different planets, and you have the transit of one and not others. So probably it's much more than this, but already you see this huge number of multi-planetary systems.
Entonces, está describiendo la máquina más eficiente para descubrir exoplanetas. Es un satélite que se llama Kepler, que va siempre alrededor de la Tierra, obteniendo fotos cada minuto de un campo en el cielo con, digamos, 100.000 o más estrellas. Y entonces, después de hacer eso durante un periodo de meses, el ordenador puede comparar la luz de cada estrella y ver los bajones, a veces 1, a veces 2, a veces 5. Entonces uno puede clasificar, esta es una estrella con 5 planetas, la otra es una estrella con 2, etcétera, etcétera. Muy eficiente.
And you see, this satellite was able to detect planets with radius smaller than the radius of the Earth. So you have a very small planet here detected by Kepler. And luckily, for this object we have the size but not the mass. And so you cannot do physics.
Entonces, Kepler es capaz de detectar planetas muy pequeños, pero solamente medir el tamaño a las muy pequeñas y no la masa. Entonces no se puede hacer física con estas detecciones, las más pequeñas.
This is the reason why, because the Kepler field in the northern sky and ARPS was in the southern sky, so we have been obliged to develop a new instrument, ARPS North, and presently located, installed at La Palma Observatory, and this is the same kind of quality, 1 meters per second. So we have decided to follow all the most interesting objects detected by Kepler. So what are the most interesting? The object with a very small mass.
Entonces Kepler observaba en el hemisferio norte del cielo y ARPS en el sur, con lo cual reproducían ARPS en versión similar pero al norte, en el observatorio de La Palma, en el telescopio Galileo, y empezaron a investigar las estrellas más interesantes donde había planetas más pequeños.
So this is a typical plot published in many different publications, but here again you have the radius, 1 Earth, 2 Earth, 3 Earth, so different, and here the mass, 2 Earth mass, 5, 7, 10 and so on. So every time you have a measurement, the radius arrives from Kepler, the mass from ARPS, so we can put symbols. And you see, and here you have the relationship. Let's imagine you have a planet extremely similar to the Earth with the same composition, but with different size, different mass. And the geophysicists are able to say, okay, if you have the Earth here, but you have twice the size will be here, it is 5, the size will be here, and so on. If you have a planet made only from iron, it will be following this line right here. If it's only water, it will be something like this, and so on. So you can have a plot where you can identify if it's a rocky planet or not. And here you see that you can find a rocky planet up to maybe 5 times the mass of the Earth. Before, people do not believe that it will be possible. And then after, eventually the sun increased because you have huge envelope and so on. So this is typically what we are doing right now.
Entonces, una de las cosas que hacen es coger un planeta, su radio de Kepler y su masa de ARPS North, y lo ponen en una gráfica ahí, y en la gráfica hay líneas teóricas que muestran cuánto sería el radio de un planeta con composición de la Tierra, y cuánto sería un planeta hecho de hierro y cuánto sería planetas hechos de agua. Y la mayoría de las medidas, que son los puntos, se caen sobre la línea que corresponde a la Tierra, básicamente. Entonces esos planetas se llaman planetas rocosos.
So just a view of the top of Parallel Observatory in Chile. You have 4 8-meter telescopes. The size of the telescope, the mirror is 8 meters. And you can use the light below the top of the mountain. And recently, 2-3 years ago, my colleague of GINEBRA built a new spectrograph, a huge one, micro spectrograph, with a goal to achieve 10 centimeters per second, so very small shift due to possible terrestrial type planet, Earth twin. And there's the possibility to collect the light coming from one telescope, or maybe, if you want, the capability to collect the light from 4 8-meter telescopes, and this is equivalent to one telescope of 16-meter telescope.
Entonces utilizaron lo que se llama el telescopio ULT en Chile, que son 4 telescopios cuyas señales se pueden combinar. Los colegas han construido un espectrógrafo que se llama Espresso, que tiene una precisión de 10 centímetros por segundo. Entonces pueden hacer medidas muy precisas de pequeños planetas y sus efectos.
So, the difficulty. This is a real image of the sun, when especially wavelengths, where you can see the convective cells, so the gas moving up to something like 100 meters per second, so very rapid. And you see that you have a magnetic activity with spores, with eruption and so on. At the same size, this is the size of the Earth. So this is the planet we would like to detect. So let's imagine the Earth is so small to move the sun, and not, when you measure the velocity of the sun, you see it's really terrible. It's very difficult. And if you really to detect the transit, it's not so better, because you have, it's not perfect.
Pues se nota entonces el tamaño del Sol y los tamaños de varios planetas que incluyen la Tierra. La Tierra es muy pequeña frente al Sol, y además las líneas espectrales en la atmósfera del Sol se forman con vientos y movimientos verticales de velocidad significativo, con lo cual extraer la señal de velocidad de una Tierra o una estrella como el Sol es no solamente la precisión, sino desentramar la física. Es muy complicado.
So, I will start to discuss what is interesting for you. This problem. Do we have the capability to detect life? First, we need to find Earth twins. So it's not so easy. Okay. And then after, how we have a chance to detect life? Let's remember, we still not have the capability to see the planet. So what we are aiming for is to detect something like this. So a rocky planet, it's a big rock, the Earth, with a small percentage, a small depth of water on top. It's very small. You can do the experiment. You take an orange with 12.7 centimeters of diameter. You put the orange in the back of water to do something like this, and what is remaining on top of the orange is more than the water on the Earth.
Entonces quieren detectar gemelos de tierra y con agua líquida, pero el agua líquida que está en la superficie de la Tierra es muy pequeña. Si, por comparación, si coges una esfera de material sólido de 30 centímetros, lo mojas en agua y lo sacudes, el agua que sigue ahí es más en proporción que las mares de los océanos de la Tierra.
And you can ask me also why we would like to have a liquid water on top of a rocky planet. The reason is not anthropocentrism, because first, water is a perfect solvent to facilitate chemical reaction, and the second point is what is one of the basic criteria of life is the capability to transfer from one generation to another one all the program to life, to function, to transfer energy, to transfer elements with the surrounding and so on. So let's imagine one single unicellular and giving this information from one generation to another one. And this is made, as you know, by the DNA. A long chain of atoms and molecules coding everything how to live. And this, if you have too big temperature, more than 120, 150, you cut this long chain and you have no life, no transmission. If it's colder than -20 chemistry is so slow, nothing interesting happens. So this is the reason why we focus our interest on this kind of object.
El agua es fundamental, además agua de forma líquida, porque el agua es un solvente ideal para todo. Además permite la transferencia de sistemas de criatura a criatura, o de célula a célula más bien. Y agua a mayor de 120 grados, por ejemplo, corta las moléculas complejas, y agua a menos 20 corta la química o ralentiza la química. Entonces, agua en forma de líquido.
So, the question we would like to answer is, what is life? Is it what is called a cosmic imperative? This was a term used by the Nobel Prize Christian de Duve, the biologist. So, what is the idea here? If you have all the good conditions, then you have a chance that life will emerge by some complex phenomena. Do we have the possibility? In the laboratory it's not possible, in theory it's not possible, so have a look and see if we can detect life around us.
Entonces la pregunta es si la vida es un imperativo cósmico, que significa si hay la posibilidad de producir vida, si se produce, básicamente, esa es la pregunta. O si es muy raro. Esa es la cuestión que ellos están intentando resolver.
So, using, for example, different techniques like I mentioned before with the transit of planets and so on, the goal is to detect different kinds of molecules believed by biologists to be critical in the development of life, because life can change the composition of the Earth's atmosphere. Ozone, oxygen, methane, and so on. So this is what will be done during the 20 next years.
Entonces, buscando las moléculas, buscan lo que se llaman biomarcadores, que son moléculas producidas por la vida, o cambios en la atmósfera en general producidos por la existencia de vida en el planeta.
And I will be very short on very few small last slide. Europe is developing a telescope of diameter 39 meters, the size of a mirror in Chile, and it is not a dream, it should be ready in 26. You can see the progress here. When I was a student, the most known telescope was the Hale telescope, 5 meters. This is this one, and this is the new telescope developed right now. It's incredible, the progress. And this is when you try to do this kind of search of biomarker, it's critical to have a lot of photons. And this was the status of the building of this telescope, the 1st of January of 2022, this year. Okay, it was delayed a little bit by the COVID, but I'm quite confident that in a couple of few years we will have this telescope in operation.
Entonces, el telescopio grande de 39 metros, el más grande obviamente en tierra, está ya en construcción en Chile. Es una imagen de su estado de construcción al principio del año 20, un poco parado por el COVID, pero ya recuperándose. Puedo añadir que España es miembro de la grupo de países que estamos miembros de esto y construyendo instrumentos para poner en este telescopio.
Maybe some of you have heard that at Christmas a couple of years ago the US sent the James Webb telescope, the follower of the Hubble Space Telescope. It's a small telescope compared to the first one, 6.5 meters, but in the space. So a lot is expected from this.
Y el telescopio James Webb, que hemos visto el lanzamiento y su puesta a punto, predicen que el día 12 de julio van a mandar sus primeras imágenes científicas. Y bueno, bien.
And thank you. Sorry to have been so late, but the imperative of the translation.
Sí. Él da las gracias, la atención y se disculpa por la longitud, pero quien se tiene que disculpar soy yo por la traducción, porque eso
Vamos a abrir un turno de preguntas, no vamos bien de tiempo, sé que vais a poder preguntar bastantes. Creo que por detrás hay alguien también con un micro, ¿no? Para no estar corriendo de allá para acá todos. La técnica es muy sencilla, ir a preguntar, levanta la mano y grita, porque yo está un poco sordo y yo también, me voy a pedir ayuda seguro y no se la voy a poder dar, o sea que intentad decirlo con fuerza.
Hello, I'm Jaime. Maybe this is a more personal question for you. And what I want to ask is, obviously you can say you're passionate about the matter of physics because of your works. What awakened that passion on you? Was it philosophy, or was the genuine feelings of physics?
Yes, I will try to answer. When I was a kid, I was fascinated by a lot of domain of science, not specifically astrophysics, astronomy. For example, I was living close to the Alps, and you have a mountain with what is a structure like this, because the pressure of continent was able to change the structure of the mountain. You can ask, how it's possible to pass the mountain and you can do something like this. And other things, I have a fascinating professor in science studying nematode. Nematode is dirty worms you have in the body and so on, telia and things like this. I was fascinated by all these things. And then after, when I was teenager, okay, theoretical physics looks fine. It was fascinating to see that you can write equation to describe phenomena. So I did theoretical physics. And then after I worked a little bit in theoretical physics, particle and things like this. And then after, in the 60s, you have plenty of opportunity to have doctoral position in different fields. And when I finished my PhD, it was you have an offer to go in the observatory of GINEBRA. Say, why? Maybe. And I went to discuss with these people. It looked interesting, and it starts like this. But I can easily imagine that if the theory, geophysicists were, we have a campaign to measure the bottom of the ocean, so I will be exactly the same interest. And more and more and more, I don't see any reason, because and all this domain benefited from huge results during the last 50 years. Okay, exoplanet, okay, but many others. For example, the plate tectonic was proven in the 70s only. So and so on. So you have no way. I mean, it's exactly as interesting. So okay, I am not disappointed to have chosen astrophysics, but I am sure that I would have exactly the same happiness in different domain of science.
Bueno, para resumir, No es un caso de persona fascinada por la astronomía desde niño, pero siempre le gusta la física. Bueno, le gustan las montañas y la orografía, estaba en Suiza, después la física teórica, y después se encontró en la Universidad de Ginebra y había una oportunidad de hacer trabajar en astrofísica y eso lo hizo. Y dice que está seguro que si hubiera sido oceanografía, por ejemplo, hubiera cogido el mismo gusto. Pero bueno, no se queja.
Buenas noches, fascinante conferencia. Primera pregunta, ¿se puede concebir la vida sin carbono a través de otros elementos químicos?
Okay, he thanks you for the fascinating talk and says, is it possible to conceive of life without water on a different chemical basis?
Probably yes, but it's always difficult to imagine what it is. You don't have so many liquids in the universe. I believe you have only two in natural condition, and water is by far the most frequent one. So maybe I cannot say not, but I would say we have a good example working. So, and we know the chemistry of the carbon is have a huge advantage on many other chemical atoms. You don't have a long change of silicium, you don't have long change of the other chemical so on. So to build a complex chemistry based on a different atom as carbon, a lot of people have tried to promote this idea. Personally, first we have to explore what is easy.
Su respuesta es que es bastante escéptico sobre la posibilidad de hacer vida de otra manera. Solamente hay un par de elementos en estado químico. Agua es el más común por la abundancia de hidrógeno y oxígeno. Las cadenas de átomos de carbono que forman vida también, nadie ha conseguido formar vida de otra manera, con lo cual él es escéptico sobre la posibilidad de otro tipo de vida. Obviamente no lee ciencia ficción, eso está claro.
¿Silicio no?
I said, obviously you don't read science fiction.
Okay. Sincerely, I believe real science is more exciting.
Estoy seguro.
La otra pregunta es, ¿cuántos exoplanetas rocosos se han descubierto hasta hoy? Y si existe un máximo de tamaño en planeta rocoso, o hay un límite que dices, no, aquí no puede pasar jamás.
I think I understood that. How many planets have been discovered up to the present time? Is there a limit in the number of planets around a single star? I think that's what he said. I may have been mistaken.
Yes, I'm not sure. I will try to. Okay, today we have all astronomers, not me, have discovered 5,000 planetary planets. Some of them, I believe, the record is a planetary system with 8 planets orbiting the same star. So this is, but I believe it's not so important because already in the solar system we have 8 planets, but we have a big body, asteroids and so on. The reality is much more complex. So I mean, this is not crucial to discover a system with 9 planets or something like this.
And the total number of planets discovered up till now?
How many? I have not checked this morning, but I mean it is 5,000 something. Well, it crossed 5,000 1 or 2 months ago.
Pues el número total hasta ahora son un poco más de 5,000 y dice que el número máximo detectados de exoplanetas alrededor de una estrella son 8, pero eso no es muy importante, en el sentido que hay otros cuerpos que no son exactamente similares aquí, por ejemplo, en el sistema solar, y además con mejor técnica, más planetas, sobre todo pequeños, se pueden descubrir. Con lo cual, that's a technique we'll discover more on that.
Well, the real interest rather the top of the priority is to find hockey planet in the habitable zone of stars. So a lot of people are trying to add. So some group prefer to find planet orbiting hosted by small star, like this is done here in Calaralto. Some of them are trying to detect planet in the habitable zone of slightly more massive star. Okay, we have a lot of work.
Muchos buscan planetas rocosos similares a la Tierra alrededor de estrellas similares al Sol. Eso es muy común. Y otros buscan, por ejemplo, planetas alrededor de estrellas más pequeñas que el Sol, y es el caso con el espectrógrafo Cármenes en Calaralto, que especializa en esto. Y hay más cosas también.
Maybe I can not forget to mention that already for more than 20 years, Spain has developed a center of astrobiology in Madrid, with a lot of people, lot of discipline, biologists, chemists, geophysics, astronomer, theoretical physicists, and so on, to try, because the question of life is not easy one. It's not one question, this is life or not. This will be a question during 20 years or something like this. It's very complex, the condition of development and so on, if it's really based on the same DNA as us or not. You have a huge set of questions from there.
Nombra el Centro de Astrobiología en Madrid, donde hay una gran variedad un equipo de personas, de biólogos, físicos, químicos, geólogos, todos combinando para buscar, incluso definir lo que es la vida, que no es simple. El proceso de buscarlo es complicado, incluso definirlo es complicado.
Hola, buenas tardes. En primer lugar, agradecer al señor Mayor la charla que nos ha dado tan interesante. Y bueno, mi pregunta iba un poco relacionada con la anterior. Y es, digamos que dada la precisión actual de la herramienta, los instrumentos de medida para detectar planetas, que tienen ciertas limitaciones, es decir, podemos medir la distancia, el tamaño, la composición y demás, pero ¿hasta qué punto tienen que evolucionar esos instrumentos de medida para tener, digamos, la certeza de haber encontrado algún tipo de vida? Es decir, no digo vida inteligente, sino digo vida de cualquier tipo. Para tener, digamos, certeza de que en algún planeta que hayamos detectado existe esa vida. Es decir, ¿qué pruebas harían falta para decir, hemos detectado al 100% que en este planeta hay algún tipo de vida, alguna forma de vida?
So, what is asking is, what would be the real proof, from our point of view, that that planet has life? That's what he's asking.
Very good question. I discussed with specialists of this question, and if you are a little bit too open-minded, it could be difficult to answer this question. If it is exactly the same copy of the life we have here, maybe we can have a clear answer. But if it is not exactly, it will be more and more difficult. So I don't know how to answer this point. Personally, I like very much to dream. You know that in the solar system, not in the exoplanet, in the solar system, you have a satellite of Jupiter called Europa. And so it's very far from the Sun. So 1 square meter is only 25 less radiation than the Earth. So normally everything should be frozen. But nevertheless, we have seen, of our satellite, have seen, that you have a nice field with water under, and no ocean still leaking at this distance. After 5 billion years, so far from the sun, you have leaking water. Why? Because you have 4 big satellites, and they perturb the orbits of the 4 satellites, and always Europa is obliged to change its orbit and change a little bit the shape of this surface. And this creates some heat inside. Since you inject some energy inside, just sufficient to maintain the water. So start to breathe. The pictures show that you have break. You have an excess of ice here. So you send a spacecraft, you take 1 cubic meter of ice. This water is coming from below. You melt this water, you filter, and you find unicellular, not big animals, unicellular. So you can start and look if the DNA is the same as our own one, and things like that. This will be more for another, I don't know, 50 years, I don't know, it will be for the future.
Pues, Rodrigo dijo que si la vida es muy similar a la vida de la Tierra, uno podría tener cierta seguridad, pero si no, no. Y después, solo un ejemplo acerca de casa, no un exoplaneta, realmente el satélite Europa de Júpiter, donde se ha detectado una capa de hielo y por debajo agua líquida. ¿Y por qué? Porque debe tener una fuente interna de calor, porque es demasiado lejos del Sol como para mantener agua líquida. Y esta fuente de calor es roce producido por su cambio de estructura, como interactúa con el planeta y con otros satélites. Y durante 5 billones de años de su existencia puede haber algo ahí. Mandas una sonda, coges un poco de hielo, lo traes a tierra y, bueno, no lo digo así, pero lo haces y después todo el mundo muere de la bacteria. Porque no tenemos protección. Bueno.
So the story is not finished. We still have some work.
Yeah, so that's what I said when you bring it back. It dies as a bacteria.
Muchas gracias por su charla y yo quisiera preguntarle, estoy aquí. Yo quisiera preguntarle, de los 2 métodos que hemos hablado para detectar exoplanetas, el método del cambio de brillo forzosamente tiene que ser para sistemas solares que están ubicando, y para si tenemos en cuenta el efecto Doppler, pues tiene mucha importancia la inclinación. Entonces, yo quisiera saber si hay algún método para detectar exoplanetas en sistemas solares que están de plano, no de canto, sino de plano, que debe de haber muchos, seguramente.
What he said was, yes, it's relatively straightforward to detect a solar system which is on edge to us with the planets going like this, but there must be many like this. So, make some comment about that.
Yeah, I mean, it's very simple. It's a problem of geometry. If you have a star like this size, a planet this size, and a period like this, what is the percentage of transit we have? And the number of planets, of transits you are missing. It's a problem of geometry. So if, let's say, you measure, I would say, 1,000 stars, and you discover 10 transits, you do this kind of geometry, and you say, okay, but the real number is 130. You have to correct this bias, yes, because it's evident you are missing all the, exactly in the solar system, you have a lot of transit of Venus in front of the Sun, but the Earth is not always at a good position.
Entonces, él dijo que hay que manejar esa situación estadísticamente. Si miras 1000 estrellas y encuentras un cierto número con planetas, para cubrir los muchos casos donde los planetas están casi perpendiculares a la línea de visión, hay que decir, hay que multiplicar el número por un factor, que es un factor geométrico que supone isotropía, básicamente. Y eso se hace, pero no se puede decir nada en concreto sobre eso, que no está, pero en contra de números sí se puede decir, hacerlo así.
¿Por ahí alguien?